Hello, welcome to my talk. My name is Hang Lee from UMass Summers. Today, I'm going to be talking about a unified framework for light spanner. This is joint work with Shay from Tel Aviv University. So what we will be, in this talk, I'm going to be talking about spanner. So what is a spanner? A T-spanner of a graph is a spanning subgraph. So as for every pair of vertices U and V in the input graph, the distance in the spanner is the most T times the distance in the original graph. What it means is that the spanner going to preserve the distances up to a factor of T. So here an example of an input graph on the left, and if we look at T equal to 3/2, then a 3/2 spanner going to be the graph on the right, which have a less number of edges. And that's why we are interested in spanner. And here in this talk, I denote M to be the number of vertices of the input graph and M to be the number of edges of the input graph. And we call T the stressed factor. And the two sort of quality measures that we're interested in. The first is sparsity, which is the number of edges of the spanner over the number of edges of the MSD, which is equivalent to the number of edges of the spanner over n-1. And the second measure is lightness, which is the weight of the spanner over the weight of the MSD. For this example graph, you can see that the spanner have 4 edges, all of the same weight, 1. So the sparsity is 4/3 in this case, and the lightness is also 4/3 in this case, because the total weight of the edges of the spanner is also 4. Okay, so sometimes we're also talking about spanner for metric spaces. And what does it mean to be a T-spanner of a metric space? Well, you can think of a T-spanner of a metric space is a T-spanner of the complete weighted graph representing the metric. For example, if I had a metric space of 4 points, then I can form a complete graph on 4 points with S weight representing the distances between these points. And then if I apply the T-spanner on the complete graph, I get a T-spanner of a metric space. So what's known about spanner? Well, a lot. Spanner have been studied for decades. And for example, in general graph, if you are looking for a spanner with stress 2k-1 for any integer k, then it's known how to construct a spanner with sparsity n to the 1/k. And if you're looking for light spanner, then it's known how to construct a light spanner, a spanner with lightness n to the 1/k over epsilon to the cubic. And for a light spanner, this stress is 2k-1 times 1 plus epsilon, what it means that we lose some epsilon in the stress to get a light spanner. For Euclidean space, we look at 1 plus, you can construct an 1 plus epsilon spanner. The stress is very close to 1 with the sparsity of epsilon to the 1 minus d, which were known in the 80s. And recently we showed that you can get a spanner with lightness epsilon to the minus d. The same for doubling metric, the sparsity epsilon to the minus order d, and thus the lightness is epsilon to the minus order d. For unit disk graph, we know a very sparse spanner with sparse epsilon to 1 minus d, but there's no report in literature about the lightness. For minor free graph, you can get constant sparsity easily because these graph itself is sparse. Minor free graph only have a linear number of edges. And if you look for a light spanner, then it's known to have a light spanner with lightness order of epsilon to the -3. So a lot have been known. And one observation is that if you look at sparsity and lightness, you can see that sparsity and lightness are almost the same for all the classes of the graph that I show here, up to a factor of poly 1/epsilon. Okay, so this is one observation that we could make about these results. And this observation brings up a couple of questions that we study in this talk. So the first question is, under which condition lightness is going to be approximately the sparsity? Because sparsity is easier, sparse spanner is much easier to construct than light spanner. And we have to have some sort of condition because it's possible to construct a family, an infinite family of graphs where sparsity is constant, but lightness is going to be linear. And so we really need some sort of condition. And there was such a condition for 1 plus epsilon strat, which is the existence of sparse spanner oracle. I would not talk about the detail of the object. You're recommended to look at our paper for more detailed discussion. And the second question that we study is, what is the precise relationship between sparsity and the lightness under the condition in the first question? When we say precise relationship, we means like precise both in terms of n, the number of vertices, also in terms of the strat, and also in terms of epsilon. Okay. So, for example, in Euclidean, we know that the lightness is approximately sparsity over epsilon. Here, if we look at the lightness of the Euclidean spanner, lightness is epsilon to the minus d, and sparsity is epsilon to the 1 over epsilon to the 1 minus d. So lightness is roughly sparsity over epsilon. So the question is, does this hold for all classes of the graph? The third question is to narrow the running time gap between sparsities and lightness. If you look at all the fast construction for sparse spanner, many of them run in linear time or almost linear time. For example, general graph, almost linear, Euclidean doubling, you need this minor free. But when you look at corresponding construction for light spanner, some of them do a factor of n. For example, for general graph, the best running time is n square. In Euclidean, you lose a factor of roughly a log n in the ACT model. And then for minor free, the best running time is also n square. So there is a gap here, and could we narrow the gap? And here's a collection of our result regarding these questions. So the first question, under which condition line is approximately sparsity? Well, we discover that when a certain cluster graph has sparse spanner, then it can construct a light spanner. We will talk more detail about this later. The second question, what is the precise relationship between sparsity and lightness? When we determine that lightness is approximately sparsity over epsilon plus 1 over epsilon square when the stress is 1 plus epsilon. So we had an extra of 1 plus 1 over epsilon square, and we also can show that this is the best possible. Because we show that there exists a class of graph where sparsity is order 1 and the lightness is 1 over epsilon square. And so when the stress is at least 2, then we can remove the additional 1 plus epsilon square term, meaning that when the stress is at least 2, the lightness is approximately sparsity over epsilon. And the third question, narrowing the gap of the running time, our framework allows you to obtain light spanner with running time almost the running time to construct sparse spanner up to a constant factor, which could depend on epsilon, and it could depend on the dimension of this metric space. But in this fast construction, we lose a lightness by a factor of probably 1 over epsilon. And here's a concrete result. For example, in general graph, we get the first spanner with lightness of order n to the 1 over k over epsilon. Recall that the previous best result is order n to the 1 over k over epsilon cubic. So we shave a quadratic factor in 1 plus epsilon, in 1 over epsilon. But you need this graph, we report the first light spanner. And for minor free graph, we get a lightness order epsilon to the minus 2. Previously is 1 over epsilon cubic. So we save a 1 over epsilon factor. It's also this is the best possible. By that we mean we construct a class of minor free graph where sparsity is where the lightness is omega 1 over epsilon square. In terms of running time, so we've obtained the first construction of light spanner general graph with almost linear time. The first construction, the light spanner for Euclidean space with order n log n time in the ACT model. For minor free graph, we get linear running time, and we also get linear time for unit disk graph in 2 dimensions. Okay, so how does our framework look like? Here's a little bit maybe a semi-formal statement, but there are more subtleties involved, which I recommend you to look at the paper. What I present here is a somewhat inaccurate version of our unified framework, but it does convey the main idea of the framework. Okay, so how does this look like? So we are given a parameter epsilon here, thing like epsilon in the strat, and any parameter L, which is the length parameter. And we are given a cluster graph where the diameter is roughly epsilon L. So the diameter of this cluster epsilon L, and the edges of the graph have a weight about L to the in the interval from L to 2L. What it means is that the weight is about 1 plus epsilon more longer than the diameter. Okay, and suppose that we are given this cluster graph, and if we can construct a T-spanner of this cluster graph, something that look like the cluster graph on the right figure, if we can construct a T-spanner of the cluster graph with sparsity F epsilon n, so this is sparsity F epsilon n, which could depend on epsilon and could depend on n, number of vertices of the input graph. If we can construct second object, remember this is a sparse spanner, so it's often much easier to construct. So if we can construct a sucker spanner for the cluster graph, then we can obtain a light spanner for the input graph with lightness F epsilon n over epsilon plus 1 over epsilon squared when the stress is 1 plus epsilon, or its lightness is going to be roughly about F of epsilon n over epsilon when stress is at least 2. So this is for the second question that we've seen before. And furthermore, if this spanner for the cluster graph can be constructed quickly, then the spanner for the general graph can also be constructed quickly up to some low order term, up to some almost linear term due to pre-processing time. Okay, so there's a lot to unpack here, but let's try to look at the first item in this application for general graph. So for general graph, if we're given a cluster graph, then and what should we do to construct a 2k minus 1 spanner? Here we're looking at strat t equal to 2k minus 1. Well, you can apply the greedy algorithm, which is a very well-known algorithm in literature, to the cluster graph. Okay, and what we get is a spanner of the cluster graph that has sparsity order of n to the 1 over k, which is what we saw in the table before. And so our framework implied that G's have a spanner with lightness the F epsilon n, which is order n 1 over k over epsilon. This is what we get from our framework. Our framework saying that when the stress is at least 2, then the lightness is f of epsilon n to over epsilon. Okay, remember here the stress is at least 2. And so we basically get the lightness is worse than sparsity by a factor of 1 over epsilon. So this is the first application for general graph. Okay. And that is the first item of this framework that allow you to obtain light spanner from sparse spanner. So let's look at the second example, which is if these sparse spanner for cluster graph can be constructed quickly, then the light spanner of the input graph can also be constructed quickly. So an illustration is to construct light spanner for Euclidean for points set in Euclidean spaces. So suppose that we are given a set of cluster with all the edges between cluster. Remember the cluster have diameters roughly epsilon times L, and the weight of the edges is about L. So how would we construct a spanner for this graph? Well, here is a classical construction in Euclidean spanner. So for each cluster C, suppose that I pick cluster C here. Then I pick an arbitrary point P in the cluster C. Okay, so the point P is a tiny point that you see here. Good. And what I do is I take a point and then I take the cone of angle epsilon around. I build the cone of angle roughly epsilon around P. Okay, so here's P, and here's all these the cone. So the first cone, second cone, third cone, fourth, eighth, so on and so forth. So the angle of each cone gonna be epsilon. Okay, so I had a bunch of cone around each point. Now I look at each edge incident to cluster, and for each cone I only pick exactly one edge. So in a cone I could see more edges. For example, if I look at this cone here, I see two edges. So the algorithms say just pick one edge. So I'm gonna remove basically one of the edge arbitrarily. So I choose to remove this edge. I look at another cone. It have two edge. I remove one. Okay, so that's the construction, and I do this for every cluster. And that's how I construct these spanner for these cluster graph. Okay, so what are the property of this spanner? So there are two property of the spanner for this cluster graph. The first is that the time to construct this spanner can be done in linear time. Basically, we just take a cluster, take a point, build a cone around it, remove edges, and this can be done linear on the number of cluster, and this is going to be order n. So these spanner can be constructed very quickly with n the number of point. And so our framework saying that when you have fast construction for sparse spanner of the cluster graph, then you could have you get a fast construction for light spanner of the input Poisson. So basically, the time to construct light spanner going to be constant time times the time to construct sparsity, which is time to construct sparse spanner, which is order n in this case, plus the pre-processing time n log n. So in overall, we get n log n running time, which is better than the previous running time by a factor of log n, roughly. And how about the lightness? Well, if it's for the spanner that you're looking at, for the spanner of the cluster graph, we can see that the number of edges per cluster is going to be the number of cone. And the number of cone is roughly epsilon to the 1 minus d in d dimension. In 2 dimension, the number of cones is 1 over epsilon, so on and so forth. So the sparsity roughly epsilon to the minus d. Well, to be more precise, the sparsity is going to be epsilon to the 1 minus d. And then our framework give a lightness which is just a poly 1 over epsilon worse than the sparsity. So the lightness is going to be epsilon to the minus d plus some constant. And this we can construct in order and log n time. The best algorithm prior to our work is order n log n square over log n in the ACT model. Here, our algorithm can be implemented in the ACT model, which is algebraic computation tree model, a popular model in computational geometry. Okay, so these are these framework, and how we could derive our framework. Well, the proof is complicated and a bit involved, so you're recommended to check out the paper. But here I give you these high-level idea. So the first idea, which is very classical in constructing spanner, is hierarchical clustering. So basically, we start with all the vertices in the first level, and then in the second level, we group them into some cluster, some of the first level vertices into cluster, and then the third level gonna be obtained by grouping some second level cluster, and so on and so forth. And so cluster in the one level gonna be the union of some cluster in the previous level. And cluster at level I had diameter roughly 2 to the power I. So level I, which is have diameter roughly is an exponential in I. Okay, so this is a very classical idea. And also, we're gonna add edges to the spanner, and the way we add it is we only add edges of length roughly to the eye. So we look at a level and we add edges along a level. Okay, so for example, we look at level I, we're gonna add some edges EI, which are between cluster level I, and the edges have length roughly to the I over epsilon, which is one over epsilon more than the diameter of the cluster at this level. And then how to find this set of edges is I. So you can guess that in our framework, we are saying that for a certain cluster graph, we construct a certain T-spanner for the cluster graph. And this is exactly the step where we use the construction for the spanner of the cluster graph. So basically, to find the set of EI to add to the spanner of the input graph, we look at the cluster graph at level I, and then we apply these algorithm to find spanner of this cluster graph. And then after we apply the algorithm, we get some edges, which is EI, and then we just add it to the spanner, and we do it for every level. So this is really the place where we use the cluster graph and the spanner of the cluster graph. Okay, and to bound the weight of the spanner, we have these. Use the idea of potential function. So basically, a potential function at every level of the clustering, we assign some potential. So the first level gonna be the potential gonna be the weight of the MST. As the level I, the total potential gonna be the diameter of all the cluster at the same level. So the potential level I gonna be the total diameter of all the cluster. And we define a potential reduction is coming from level I minus 1 to level I. How much potential is reduced? So we denote by delta I, which is potential of the previous level. Phi I minus 1 minus the potential of the current level. And what we are able to show is that the total weight of these edges that you add at the level I, so EI gonna be these edges here that we add at level I, the total weight of the edges we add is constant times the sparsity times the potential delta I over epsilon plus a low order term. Okay, the low order term appear only for the step of t equal to 1 plus epsilon. When the step is bigger than 2, we don't have this low order term. That's the key theorem. The proof is going to be in the paper, so check it out. And now all we have to do is to sum up all the weights of these edges that we add at every level, which is going to be the weight of total the potential reduction plus the weight of a low order term. And you can see the potential reduction here. We had a telescoping sum, which is at most the sum of all these potential reduction going to be at most the potential at the first level, which is the weight of the MST here. And so we have that the total edges out is order of the sparsity times the weight of the MST over epsilon plus the low order term. The sum of all low order term gonna be weight of MST over epsilon square. Okay, and so that's why when you divide the weight to the weight of the MST, which is defined by the Linus, then we get Linus equal to order sparsity over epsilon plus 1 over epsilon square. And this is for step 1 plus epsilon. And when t equal t at least 2, like I said before, we don't have this low order term. So you get a Linus equal to sparsity over epsilon. And that is the proof, the basic idea of the proof. Okay, so I have 2 open questions. So in general graph, we show that you can get 2k minus 1 times 1 plus epsilon spanner with Linus order n to 1 over k over epsilon. So the first question is, could we get rid of the epsilon here? Meaning that could we show that there exists a 2k minus 1 spanner with Linus order n to 1 over k? I personally believe that epsilon should not be there. And the second question. We show in the papers that line is approximately sparsity over epsilon plus 1 over epsilon square when t is 1 plus epsilon, and line is the sparsity over epsilon when t is at least 2. That's what we show. But the running time to get these line spanner with this very small line is not linear. Okay, we had a fast construction, but in the line we lost more than 1 over epsilon factor. We are, in fact, in the Linus construction, we lose probably 1 over epsilon cubic. And so the question is, could we improve the running time of the algorithm that obtains this precise relationship between sparsity and Linus? And thank you for attending my talk.